Okay, number one, they want you to find all of the roots of the equation. Now, it says without using a calculator, but what it means by that is don't use the second trace zero function as proof that particular zeros are zeros or are roots. But we can look at the graph to sort of narrow down the roots that we would use to break down the polynomial using synthetic division. So we enter that in, and we see that it goes through the x-axis. It looks at 3. So let's do second table and check to make sure when x is 3, y is 0, and it is. So what we're going to do is we're going to use 3, and we're going to use synthetic division and break this down. So we have 1, 3, 0, 0, 1, 3. And over here, this is your proof that 3 is a root. So right now we have x minus 3 times x squared plus 1. And the reason why it's x squared plus 1 is because there's your constant, that's your x squared. So 1x squared plus 1. And then the x minus 3 comes from the 0 of 3 here. So how do I get all of my roots? Well, 3 is a root. We know that. But I know that I need 2 more roots because I'm supposed to have 3 of them. Well, the other 2 roots you can get from this quadratic. Because there's no x term, what I can do is I can just set this equal to 0 and solve. So it's positive negative I. So those are my 3 zeros. So you subtract 1, you take the square root of both sides, positive negative root negative 1, and that's the definition of I. So we're going to do the same thing here. I'm going to graph it. Okay, I just plugged that all in. I just paused the video while I did that, save some time. And the graph over here looks like it goes through 2 of these, here and here, maybe negative 1 and negative 3. Let's check the table. Negative 1 is a 0 and negative 3 is a 0. So we can use both of those to decrease this 4th power down to a 2nd power. So negative 3 and negative 1. So we'll start with negative 3. We have 1, 4, 7, 16, 12. Let's do this out. So we know that negative 3 is a 0. Then we'll use these, and we'll use negative 1. Alright, so that proves that negative 1 is a 0. So what we want to do now is write this out in factored form. So we have x plus 3, x plus 1, and this is my constant, my x squared plus 4. So to get my other 2 zeros here, because we have 2 of them already, negative 1 and negative 3, to get the other 2, we'll do just like we did with number 1. We'll set this equal to 0 and solve for x. So if we extract the I and the square root of 4 is 2, we get positive negative 2i. So my roots are going to be negative 3, negative 1, and positive negative 2i. We have 4 roots for the 4th degree polynomial. Find all the zeros of the function. Again, for this one, we're going to type in the equation. So I'll do that now. So I typed it in and it's graphing now, and it looks like right over here we have, looks like positive 4 might be the 0. So let's just double check on the table. Scroll down to 4 and we see that it is a 0. So we're going to use that to break this cubic down to a quadratic. And it works. So we have x minus 4 times x squared minus x plus 1. That's what this is right here. So because this has an x term, I just can't set this equal to 0 and solve for x. What I have to do is use the quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. I'm using a as 1, b is negative 1, and c is 1. So we're going to have 1 plus or minus. This is 1 minus 4, which is negative 3. So this is 1 plus or minus I root 3 all over 2. So here's 2 zeros in addition to positive 4. So we have 4 and 1 plus or minus I root 3 all over 2. So here are your 3 zeros right here. Number 4, they want you to find the complex roots, or state the number of complex roots, possible number of real roots, and the possible rational roots. The number of complex roots is equal to the degree of the function. So the number of complex is going to be 4. The possible number of real roots is equal to the degree, or less than that by an even number. So 4, 2, or 0. And the possible rational roots, and now again these are possible, we're going to do the p over q. So we're going to have positive negative 1, 2, 13, and 26 all over positive negative 1, positive negative 2. And the master list would be positive negative 1, positive negative 2, positive negative 13, 26. And we have 1 half. 2 halves is 1, 13 halves is another one. And 26 halves is 13, right over here. So here's my master list right there. Number 5, find all the zeros of the function. So I'm going to type that in. So I typed it in and it's graphing now. We see that looks like it bounces off, but there's a chance that it might not be bouncing. And over here, it doesn't look like it goes through at 2. So what we're going to have to do is we're going to have to zoom in and see what's going on over here. So we'll do a zoom box right around here. Alright, so you see it crosses the x-axis just before the negative 2, and then it goes through negative 2. So if I look at my table, I see that my negative 2 is going to give me a 0. So that will make me, well, that will, after synthetic division, drop this to an x squared. So that's what we're going to do now. Let's use negative 2. Write down the coefficients, and then synthetically divide. Okay, so we have x plus 2 times x squared minus 5. So because this doesn't have an x term, I can just take that and set it equal to 0. And we have all our roots. So we have negative 2 as a root, and we also have positive negative root 5. Those are your 3 roots. And we have another one where we have to find all of the roots. So let me type that in now. Alright, I typed it in, now it's graphing it. We had zoomed in pretty far last time, so let me just zoom out. Alright, so it looks like we've got a couple zeros here that we can use to drop this down to a squared. Let's just go to the table. We see that we can use -3, we can use -1, and we can use 3. That will give us the entire, all of the factors. So -3, -1, and 3. Let's use those 3. So let's try -3 first. So that proves that -3 is a root. The next one was -1. Let's put that into the quotient here. And that proves that -1 works. And then let's use 1, because that was the third one that worked. Wait a minute, did 1 work? No, 1 didn't work, 3 worked. Let me just erase this here. It was 3 that worked. Okay. So, if I write this in factored form, we have x plus 3, x plus 1, x minus 3, and 2x plus 1, all equals 0. So the list of roots are going to be -3, -1, 3, and if I set this equal to 0, you get -1/2. So those are your 4 roots. Alright, number 7. Find a 4th degree polynomial with these roots. So we're going to have 2i and -2i in addition to -3 plus I and -3 minus I. So what we're going to do is we're going to build our quadratics here. We're going to take and lump those two and those two together. So the conjugates I'm going to lump together. So this one's going to give me a quadratic, and this one's going to give me a quadratic. And together that's going to give me my polynomial. So if I add these together, I get 0. So that's going to eliminate the middle term. If I multiply these together, I get -4i squared, which is +4. Again, we're using the idea of building a polynomial from the sum of the roots and the product of the roots. Over here, if I add them together, I get -6, so the opposite of that is +6. And if I multiply these together, I get 9 minus I squared. So 9 plus 1 is 10. So there's my quadratic for that. So what I'm going to have to do now is I'm just going to go through and multiply all of that together. Then my result is going to be the polynomial function. So if I distribute the x squared in, I get x to the 4th plus 6x cubed plus 10x squared. And then I distribute the 4 in, so I get this. So if I add like terms, I'm going to get 14x squared, 24x plus 40. So that's going to be my polynomial function. Determine whether a quadratic model exists. Well, if you were to plot those 3 points as a scatter plot, they do not form a straight line, so a quadratic model does exist. So if you hit Stat Edit and you clear out L1 and L2 here, and enter -4, -5, and -6 for L1, L2, sorry, for L1, and 11, 5, and 3. For, whoops, I gotta go over to L2. 11, 5, and 3. And then go to Stat, calculate the quad reg, and hit Enter. They're going to give you your A, B, and C values. So your A is 2, your B is 24, your C is 75. So it's f of x equals, the A value is 2, so 2x squared, then it was 24, then it was 75, I believe. So you just use your A, B, and C values for your A, B, and C variables of the standard form of the quadratic. Number 9. We have an I in the denominator. We can't have that, so we're going to multiply the top and bottom by the conjugate. So if I multiply the top, I'm going to get 18 plus 6i. The denominator, they're conjugates, so I'm going to multiply the f, which is 36, and then the L is -4i squared, which is positive 4. So 18 plus 6i all over 40. And that can be reduced by a factor of 2. 9, 3, 20. So 9 plus 3i all over 20. Number 10, a fourth degree polynomial function has zeros at 3 and 5 minus I. Well, 5 minus I is imaginary, so we automatically know that 5 plus I has to be a root of this fourth degree polynomial. Because it's a fourth degree polynomial, we know that it's going to have 4 total roots. 3 of them are here. That means this fourth root has to be something real, and the reason why, well, it not only has to be real, it has to be real and rational, because if it was irrational, not only would you have this, you would also have its conjugate, which would make this 5 roots. And it can't be imaginary, because if this is imaginary, let's say it's I, you would also have to include its conjugate -I, which would make this to have 5 roots again. So them saying, can 4 plus I also be the root? Well, if it was 4 plus I, you'd have to add 4 minus I as also being a root, which would make this 5 roots, which would go against the idea that, well, it's the fundamental theorem of algebra. You've got 4 roots for a fourth degree polynomial, so 4 plus I cannot be that last root.